4.1 and 4.3, we have a brand new chapter, and this is the last chapter we're going to deal with. Oh, I know. But it is trying to use derivatives in such a way that we can better understand functions and what their graphs look like. So the idea is that when we have a polynomial function, or any function that's continuous in an interval, we know it has its ups and downs, right? Well, if it has its ups and downs, I don't know, just random graph, then these points would be really useful to know about. Not just those, but also the y-intercepts and the x-intercepts, and also like where it kind of does this downward-looking curve versus an upward-looking curve. And not down. This is an upward-looking curve down here, and then it's a downward. It's just interesting where the curves change from like this to this. That helped. I don't think it did. But anyway, all we're going to look at right now, though, in 4.1 through 4.3 is these points. Now these two, let me point to them, are called local mins and maxes, or we call extrema. That's the plural form. Anyway, this is a minimum, this is a maximum, because it's the highest in his little neighborhood, and this is the lowest in his little neighborhood. This guy, though, would be called an absolute max, because he's the highest point in the whole graph. See, this goes down at this point, and this goes down at this point, so there. There is no absolute minimum, because it goes all on down to negative infinity, right? So it can have absolute maxes and mins. It might have local absolute mins and maxes. Local mins, local maxes. It might not have any. It's possible. So how do we know where these are? Well, if you remember about tangent lines, as we get close to these, the tangent line becomes horizontal. We had problems on the last chapter where we looked at that. So the idea is that we want to find the derivative and then set equal to 0. And solve. That's the idea. All right, so number 1. And these, when they're finding absolute extrema in an interval, then we just need to look at numbers that fall in that interval. So in this case, it writes 2 less than or equal to x less than or equal to 5. And another way to write that with interval notation is 2, 5, like this. And this is the way I write it in the quiz. So just so you know, that's what I mean. So what the idea here is I'm going to find the derivative of this guy. I'm going to set it equal to 0. I'm going to solve. But then any answers I get that's not between 2 and 5, I'm going to throw away. I don't want them. I don't care. So let's do that. Let's find the derivative. G prime is negative 2x plus 7. That's not too bad. I'm going to put a little arrow instead because I'm going to set it equal to 0 now. So this is a linear equation. Yeah, you guys remember how to do those, right? Subtract, and then divide, and you get positive 7/2, which is 3.5. There we go. Yeah, and 3.5 falls in this range, this interval. Sorry, I shouldn't say range, that's for y values. Anyway, so this one we do care about. We care about this one, but we also care about these two. Now we're including 2 and 5, so we kind of care about what y values we're getting. And that's the point. The extrema values are y values, not x values. Where they are the x values, but the values themselves are y values. So all I have are 3 x values, and that's not answering the question. And it says find the absolute extrema values. I need to plug these 3 numbers back into the original equation. So g of 2, the derivative is done. Let's just put a little, keep it separate. But g of 2 would be this thing, negative 2 squared plus 7 times 2 minus 10. And that's going to be negative 4 plus 14 minus 10. And that's going to be 0. Cool. All right. 3.5, plugging it in. I'm going to use the fraction form because I don't have a calculator handy. let's see, negative 7 halves, so I'm going to put 7 halves squared plus 7 times 7 halves minus 10. And that's negative 49 over 4, and that's positive 49 over 2. That's 10 over 1. See, I'm going to have to find a common denominator. Times 2, and this is times 4. So this is going to give me negative 49 plus 98. And then minus 40 all over 4, right? Common denominator. And that's 49 minus 40, that's 9/4. Okay. And then last we have g of 5. Yeah, there's a lot of work with this, you know, especially by hand. So we're going to plug in negative 5 squared, say plus 7 times 5 minus 10. And then that gives us negative 25 plus 35 minus 10. And that, again, is 0. So our extreme values, if we want to write this as our answer, we say absolute max is the highest of these three numbers, and that's 9/4. Or if you want to say 2.25, you can. And at is the x value that gave it to us. So at x equal to 7 halves. So I don't know, you know, calculus, we like fractions better than decimals. You can leave it in decimal, that's perfectly fine. And the absolute min is going to be 0, because those are the smaller of the three numbers. And that's at x equal to 2 and x equal to 5. That's how we do number 1. That's a bunch of writing, yeah, I know. But, you know, it is what it is. Sorry about that. But it's not like difficult work. Like related rates has been difficult, maybe chain rule has been difficult, trig derivatives, but you know, oh, there's a trig derivative coming, and that's okay. So the thing about trig functions is if eventually, remember, the rules are find the derivative, set equal to 0, and solve. So we're going to be solving trigonometric equations. You might have to go back and look at that in your notes for trig, or even at the beginning of the semester we talked about it briefly. And if you need more, you know, you can find supplemental videos on solving trig equations on Google and YouTube, yeah. All right, so f of x equal to cosecant of x, we're going to find the derivative. Put a little arrow. And the derivative of cosecant is negative cosecant cotangent, correct? Okay. And that's going to be equal to 0. Okay. Now, in order to solve this problem, oh, I forgot the range. The range is negative pi over 2 to 3 pi over 2. All right, so these two numbers I'm going to have to look at when I plug into the original. But the other one's going to come from this equation right here, this guy. Okay, so how do I solve trig equations when I have two different functions like this? Well, if they're equal to 0, I can use the zero product principle and just split them up. Right? So all I need to do is find x values whose cosecant is 0. And that means I have to think about, well, what does that mean, cosecant? So like 1 over sine is another way of thinking about it. And the negative don't matter if there's a 0 on the other side, right? Okay, so what number can I plug into here so that I get 0? 1 over something gives me 0? No, not 0. Answer is nothing. Nothing. I can't plug anything, so I got none from this. For this one, I've got to find what numbers give me a cotangent of 0. Now, there are some numbers in this one. One way I can think about it is 1 over tangent, maybe. But that's not the only thing. You can also think of it as cosine over sine equal to 0. So I really care about what makes him equal to 0, because that's what would work. Now, if it made both cosine and sine 0 at the same time, that'd be bad. But there is no such number. So we're okay there. So let's find out what makes cosine 0. That is pi over 2. Right? That's pi over 2. And that's in this range. Also negative pi over 2 does. And also 3 pi over 2 does. But those are already included. But 0 and pi would make sine 0, and that's no good. We don't want that. We don't want to divide by 0. So this is the only one. So these three. Trig equations. All right, so let's go f of negative pi over 2. That's going to be whatever the cosecant of negative pi over 2 is. Well, it's like saying 1 over the sine of negative pi over 2. And that's negative 1. So the answer is negative 1. Positive pi over 2 would be the cosecant of pi over 2, which is 1 over the sine of pi over 2, which is 1 over 1, or 1. And then f of 3 pi over 2 is going to be the same thing as negative pi over 2, negative 1. Okay, so here are my three numbers, negative 1, positive 1, and negative 1. So we have an absolute max is positive 1 at x equal to pi over 2. And we have the absolute min is negative 1 at x equal to negative pi over 2 and x equal to 3 pi over 2. Yeah. Okay, so it's very similar to this. You know, we had one number that we found, and that number got included with the original 2 in the interval, and we plugged all three of them into the original equation, and we got answers, and those answers were the mins and maxes, 1 and negative 1. Where they were the numbers we plugged in. Okay. Number 3. With number 3, we have an inverse function. That's not the right word. What's it called? Rational function. Yeah, I figured it out. Okay. But anyway, a rational function has some issues. Like, for instance, if you plug in 0, you're dividing by 0. That's no good. But their range goes from 0.5 to 3. So we don't have to worry about 0 as a problem. You know, there's an asymptote there, but we're not even looking at that range, that domain. That's the right word, okay. All right, so if we want to do the derivative of this, I don't want to do quotient rules, so I'm going to rewrite this as negative 3x to the negative 2. Yeah, x squared comes up as negative. And then I find the derivative. So multiply down, get positive 6. Subtract 1, we get negative 3. And that's the same thing as 6 over x to the third. And when I set that equal to 0, then I have to figure out what numbers can I plug into x so that this is true. Well, there is no such number. There's no number I can plug into x to make this equal to 0, because it's 6 over a number. And that means that there is no absolute mins or maxes in between these two numbers. But I still have these two numbers to check. So f of 0.5 is going to be negative 3 over 0.5 squared. Now I need a calculator. All right. Delete. So 3 divided by parentheses 0.5 close raise to the second, close parentheses. Looks like 12. Negative 12, sorry. Okay. And then the other one I have is 3. So negative 3 over 3 squared would be negative 3 over 9, which is negative 1 over 3. Okay, so one of them's big and one of them's small. So we have an absolute max, that's what I usually go with first, is negative 1/3, right? It's closer to 0 than negative 12 is, so it's bigger, since we're in the negative land. And it's at x equal to 3. We have an absolute min is negative 12 at x equal to 0.5. Yeah. So when there's an interval like 1 through 4, then you always have an absolute min and max. You always do. Even if you don't find any in your derivative work, you always have these two numbers to plug in, and one will be bigger and one will be smaller. Now, it is possible, I should say that, it is possible that if you plug both of these into the original equation and you get the same answer, that you have to figure out if they're mins or maxes, because they're the only two things you have. So let's say, oh God, I can't even think of one where it does that. So let's say between 0.5 and 3, it went up, and then there was an asymptote, and it went like this. So this would be a min, but not an absolute min, and this would be a max, but not an absolute max, because there's bigger numbers. So really, in that case, you wouldn't have a absolute min or max. Just thinking out loud. Don't worry, I'm not throwing those at you. Oh, wait, I maybe spoke too soon. Here's tangent of x, which I know has asymptotes. And we're going from negative pi over 4 to pi over 6. So the question is, where are those asymptotes? Right? This is sine over cosine, so wherever cosine is 0, that's pi over 2. And negative pi over 2. So this is in the fourth quadrant, this is in the first quadrant. I don't think we hit those asymptotes, so we're fine, we're fine. Yeah, like I said, I'm trying not to throw those at you, those weird ones. So here we're going to find the derivative of tangent, which is secant squared. A little arrow. And I'm going to set that equal to 0. Now, anytime I've got a square on a trig function, if it's a trig equation, I can just take the square root of it, both sides, and that'll get rid of it, the square. Square root of 0 is 0. Plus or minus 0 if you're really feeling classy. Anyway, secant equal to 0 means I've got to figure out what angles have a secant of 0, and there are none. Again, because this is like saying 1 over cosine equal to 0. And that means that it's not possible. Okay, so we're just dealing with these two again. F of negative pi over 4. It's like saying, what is the tangent of negative pi over 4? So if I remember my chart correctly, this is the square root of 2 over 2. It's for pi over 4. No, wait, tangent is sine over cosine, and that would be 1. They're both square root of 2 over 2. But this is in the fourth quadrant, and tangent is negative in the fourth quadrant. Okay. Pi over 6 is like saying 30 degrees. So it's saying, what's the tangent of 30 degrees? And in this case, the tangent is sine over cosine, and that's 1/2 over the square root of 3. So this is 1 over the square root of 3. Yeah. Which, also is written as square root of 3 over 3 for those of you who remember your trig. So the absolute max is going to be the positive one at x equal to pi over 6. And the absolute min is going to be negative 1 at x equal to negative pi over 4. Now, I'm being pretty cavalier with these, so let me go check my answers, number 1 through 4. So yes, okay, number 2. All right, so let's talk about number 2. So I found answers, but I think what I was talking about happened. So let's think about one of the graph of cosecant, okay, from negative pi over 2 to 3 pi over 2. Okay, so this is the inverse of sine. So I would have a 0 here for sine, which means I have an asymptote for cosecant. And then it goes up to 1 here. So it's still going to be 1 for cosecant because the inverse of 1 is 1. And then it comes back to 0, so I have another asymptote. And then it comes back to, it's negative 1 to here. So it goes up, middle, down. Yeah, and then it comes back to here. Wait. No, this is an asymptote. 0. This is negative 1. Okay. Sorry. Okay, so in between these two, there are two asymptotes. So the graph looks like this in this range. And that means that even though I found negative 1 and positive 1 as my two values, 1 is actually a minimum, and it's not an absolute minimum because it's lower than anything in its neighborhood. So because all the numbers go up to positive infinity and some of them go down to negative infinity, none of that is right. there are no, I'm just putting none. That's the right answer. So number 2 is none because of the graph of this guy. Now this is the one I was saying I was going to try to avoid giving you. So I'm not even sure. I may have put this on the dang quiz. Who knows? I'll have to go back and look. But this one is correct. And this one is also correct. Okay. So 1, 3, and 4 are good examples. And number 2 is the tricky one. My bad. Number 5, 6, and 7, and 8. They all ask you to find the extreme value. So they want local mins and maxes. And they don't give you an interval like they do here. They just say anywhere from negative infinity to positive infinity. So we're going to do the process. Y equal to x squared plus 2x minus 3. We're going to find the derivative. That's 2x plus 2. We're going to set it equal to 0. And ooh la la, subtract 2. Divide by 2, we get negative 1. And that's the only one that I can plug into the original equation. Now, here's the thing. Y equal to negative 1 squared plus 2. I'm sorry, it's not the thing yet. Hold on, let me find the value. It's 1 minus 2 minus 3. And that is negative 4. So is this a local min or a local max? That was me shrugging on video. I don't know. So here's a trick. This is a thing called first derivative test. So the first derivative test, you're going to draw a number line like so. And then the x value that you found goes on the number line. And if you want it to be slightly off center over here because it's negative 1, that's great too. It just doesn't matter if this is the only one. This is the only one you care about. So now what you're going to do is you're going to plug in any number you want to on the left and on the right side to see what's going on. Are these values bigger or smaller than the value here? Now another way to think about that is by plugging these numbers, just one number, any number you want. So like, let's say negative 2. Plugging that into the derivative would be 2 times negative 2 plus 2. That's negative 4 plus 2, and that's negative 2. So I would put a minus sign right here. What this is telling you is that the derivative is negative for any number I plug in that's to the left of negative 1. And what that means is that since the derivative is negative, the slope is decreasing. The slope of the tangent lines is decreasing, so the graph is going down. So I can draw a little arrow like this towards the negative 1. All right? Now I plug in a number over here that I want to, let's say positive 2. I don't know, just for fun. I could also plug in 0, 1, whatever you want. 10, a million, I don't care. This is you plugging it in though, into the derivative. So 2 times 2 plus 2 gives me 4 plus 2, and that's 6, and that's positive. So that means that the tangent lines are increasing, going up. So from there, I'm going to draw a little arrow like this. So if I were to draw a graph, it would curve down and then would curve back up at negative 1. It's like a vertex. Hey, this is a quadratic equation, isn't it? It's a parabola. And this first derivative test just told me that it was going down to a vertex and then going back up. Yay, algebra and calculus coinciding. All right. So this is a minimum. So we say negative 4 is an absolute minimum at x equal to negative 1. Okay. Now we know it's an absolute minimum because we can imagine the graph and it only goes up from there. So this is the lowest point out of all of them. But if it had gone from down here up and then came back down and then went back up, this would be a local min because it came down from negative infinity all the way over here. But not this case. This is just a parabola. So absolute minimum. All right. Number 6. Y equal to x cubed minus 3x squared plus 1. This is a polynomial with a degree of 3, so it's going to look like ju, 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 or it's going to look like ju, ju, ju. And that's what I remember from some algebra class in my past somewhere. But you don't have to know that. What you can just do, go through the process. Y prime, we got 3x squared minus 6x, that's 0. All right, that's the derivative. And then we set it equal to 0, and we solve. Well, I can solve this by factoring. Ooh, 3x, and then I divide, I get x minus 2, right? If you distribute, it's the same thing. And then I can split those up, 3x equal to 0, and x minus 2 equal to 0. This is solving a quadratic equation, by the way, so you need to know how to do that. Anyway, you get x equal to 0, and you get x equal to 2. So you have two numbers. So now we have to plug them both in. So we get y equal to 0 cubed minus 3 times 0 squared plus 1, and that's going to be equal to 1, okay? And then we also get 2 cubed minus 3 times 2 squared plus 1, and that's going to be 8. See, 8 minus 4 times 3 is 12 plus 1. It's negative 4 plus 1 is negative 3. Okay. So one is a max and one is a min, and it might be okay to say, hey, this one's bigger than this one, so this is probably a max and this is probably a min. And be right as long as we have a continuous function everywhere. There's no asymptotes. And in this case, that's true. So you'd be right. But let's not do that. Let's do the first derivative test with both of these two numbers. Now, the first derivative test, the x numbers go on the number line in order. So 0 comes before 2. And then you pick numbers to plug into the derivative. So these two numbers, by the way, these two numbers go into the original equation. And then any number you pick down here in the first derivative test go in the derivative. So like negative 1, you'd say 3 times negative 1 squared minus 6 times negative 1. That is 3 plus 6. That's positive. So notice I don't really care what the number is. And it might be good just to not finish it. Don't write 9 because maybe you get confused and think, oh, 9 needs to be in my answer somewhere. No. All this is a test. And it's only telling you if it's positive or negative. So I'm going to draw a little arrow like this, going up. All right, 1 goes here, so I'm going to try 3 times 1 squared minus 6 times 1. And that's 3 minus 6, and that's negative. So this is going down. And then this one's probably going up, but let's check. Something like 3. And we get 3 times 3 squared minus 6 times 3. Always plugging these three numbers into the derivative. And we get 27 minus 18, and that's positive. Yep, you're right. Okay, so it goes up, then down, then up. So that means that 1 is a... So if it's going up at the end, it's going up towards positive infinity. And if it's going down at the beginning, it's coming from negative infinity. So there's no absolute min or max. These two numbers, 1 and negative 3, these values are locals. They're just locals. They're not superstars. They just, you know, the town knows who they are and local celebrities, you know. So 1 is a max, local max. You don't have to say at, never mind, necessarily. And then negative 3 is a local min. Okay. And if you want to, you can write them in point form. So this 1 can be written as 0, 1, and this negative 3 can be written as 2, negative 3, if you want. You know, that might be a better way of showing it. All right, number 7. Oh yes, the irrational function. 1 over y, x squared. What in the world? It's late. 1 over x squared minus 1, and in this case, I'm going to take the derivative, but if I want to do this derivative, I'm going to either have to choose between quotient rule, or I can bring up this whole thing with a negative 1 power and do chain rule. What do you like? I like chain rule. So check it out. Right? And now when I take the derivative, I'll bring down the negative 1, outside derivative, right? Subtract 1. And then the inside derivative is 2x. Throw that x squared minus 1 back in there. And there you go. I just have to clean it up, right? So let's bring this stuff down. So we got negative 2x up here, negative 1 and 2x combined, or multiplied, sorry. And then down here I have x squared minus 1 squared equal to 0. Okay. Now, when you're solving a rational equation, for the purposes of what we're looking for using the first derivative test, we want to find not only where it's equal to 0, but also where it is undefined. In other words, this will split into negative 2x equal to 0, and it'll also split into x squared minus 1 squared equal to 0 to find our numbers that we're going to put on there. Actually, if you want to, you can put not equal to 0 just to make yourself feel better, because that, can't happen. All right, divide by negative 2, you get 0. Take the square root, you get 0. Add 1, you get x squared not equal to 1. And then when you take the square root, square and square, so we got the square root twice. We get x not equal to plus or minus 1, don't forget. So here's the thing about this. So with rational, these numbers go on the number line in the first derivative test, but you would not plug them into the original equation, 1 over x squared minus 1, because they're going to give you 0 in the denominator, which means undefined. So I don't have to plug those in. I just have to plug in 0. 1 over 0 squared minus 1 is negative 1. Now, is it a local min or is it a local max? Let's look at the first derivative test. Negative 1, 0, and 1. So we want to plug in numbers in 1, 2, 3, 4 different areas of this number line into the derivative, which is this guy. And it might help you to put a little bubble around the derivative, the finished derivative, the clean derivative. You know what I'm saying? So let's look at negative. Actually, you know what? 0 is the only one we care about, right? So I don't even really care about what's going on over here and here. I don't care. All I care about is what's happening around 0. So let's say that we plug in negative 0.5 into the derivative, or negative 1/2 if you like that better. So that would be negative 2 times negative 0.5, and this would be something that's positive. Now look, I could work it out, but I don't have a calculator. I'm trying to quicken my time here. So look, negative 0.5, it doesn't matter what I plug into this. If I square it and subtract 1 and then it's all squared, it's going to be positive. And so really all I care about what's happening up here in the top. Is it going to be positive or negative? This is going to be positive. Positive divided by positive is a positive. So it looks like it's increasing before you get to 0. Now let's try something like 0.5. Here we would have negative 2 times 0.5 over a positive thing, and that's negative over a positive. It's negative, and that's decreasing, yeah? So I know that this is a local max. Local max. It might be an absolute max, but let's just call it a local max and not worry about that too much. And if you really want to look into it, let's see what's going on over here. You plug in negative 2, and you get a positive. Plug in positive 2, and you get a negative. So it looks like it's increasing and then increasing some more, and then decreasing, decreasing. But I know that here has 2 asymptotes. So if I really wanted to look at this graph, it would look something like this. Right? And we have plugging in 0 gives me negative 1. So 0, negative 1 is this point right here. And we know that it increases to that point and then decreases from that point to there. Here's something else I know. If I plug in something like negative 2 into the original, I'll get a positive number. So all these numbers are positive. No matter what number I plug in, it'll always be bigger than 1. So what's going on here is that it's increasing the whole time. So it's going off to positive infinity here. And then over here, same thing. If I plug in anything like positive 2 into the original, it'll be positive, but it'll look like this. It's decreasing the whole time. So it's coming from positive infinity. It's going towards negative infinity down here. So there is no absolute min or max. This is the only thing that I actually have a local min or max. Everything else has asymptotes, and that's what it looks like. That's how you draw that guy. Just knowing from the first derivative test. Isn't that cool? Okay. Number 8, I'm tempted to tell you to skip it, but you know what? I know it's not on your quiz. Let's do it anyway. So here we have x squared plus 2x plus 2. And really, I really would like to do is factor and cancel right away if I could, but I can't. So look, this is probably best if you do quotient rule, which is weird but true. So let's say x plus 1. Oh, wait. Yeah. I'm gonna do the cross multiply thing. I don't remember what I said about that when I did the video, but here you go. Here are the derivatives for the top, derivative for the bottom. Now I'm gonna do cross multiply down, starting with him, and I'm gonna have y prime is 1 times that thing, x squared plus 2x plus 2, minus x plus 1 times that thing, 2x plus 2. All over the derivative, the denominator, sorry, squared. No, you can't cancel 1. Stop that. You do need to FOIL this out. So let's do all that business. Let's see, we have x squared plus 2x plus 2 minus 2x squared minus, I'm going to distribute the minus sign throughout. X times 2x is 2x squared. X times 2 is 2x. And then another 2x makes 4x. And then 2. Okay, and all that's over blah, blah, blah. And then I'm going to combine like terms. I get negative x squared. And then I got negative 2x. And then the 2's cancel. Well, that's nice. Over, and now I'm going to write x squared plus 2x plus 2 squared. All right, so there's a lot of algebra to do with this problem. That's why I was like, I'm not going to make him do that on the quiz. But the thing is, you're still going to set this guy equal to 0, and so that means that we're going to set the top equal to 0. And we're going to set the bottom not equal to 0, just like before. Okay, so this guy, we're going to factor. Remember, that's how we do quadratics and polynomials. We pull out a negative x, and we're left with positive x plus 2. Yeah. So that's going to give me x is 0 from him. The negative doesn't count. And then x equal to negative 2 from him. All right, so I got 2 numbers. Over here, take the square root, get rid of that. Now I have a quadratic equation that doesn't factor. So I have to use the formula. X is equal to negative 2 plus or minus square root 2 squared minus 4 times 1 times 2. Uh-oh. All over 2a. So this is going to be a negative number, and that means not real. So I don't care. So nothing to worry about here to put on the number line. Just these 2 numbers. So let's go to those 2 numbers. 0 and 2. All right. Now, where is that darn derivative? Here he is. Put a little bubble around him. Okay. Now, once again, we have this denominator being squared, so it doesn't matter what I plug in, the bottom's going to be positive, right? So it really matters what's happening up top. So let's look at, let's say, negative 1. That's what I like over here. Plugging in negative 1 into this, we get negative times negative 1 squared minus 2 times negative 1. That means that'll be positive 1, but that negative will still be there. These 2 will make a positive 2, so it's positive, right, over positive. So it's going like that. Let's plug in 1. That's nice. So we get negative 1 squared minus 2 times 1. That's negative 1 minus 2, and that's negative. So that's going down. And let's plug in 3. See what happens. We get negative 3 squared minus 2 times 3. This is negative 9 minus 6. That's also negative, so that's going down. So here's a funny thing. So before, when we had those numbers, and I should keep this around. Here we have those numbers, negative 1 and 1. I didn't care about them because they were the things that made the original function's denominator equal to 0, undefined. Right, well, both of these numbers work in here. 0 plus 1 is fine, 0 plus 0, 2 is fine. Same thing with 2. If you plug 2 in, it's all positive, so you're going to get a number. So I care about these 2 numbers. But what happens when it's decreasing and then keeps decreasing? Well, that means this guy has no min or max. If it's both decreasing on either side or both increasing on either side, it has no min or max. So the only one I care about is this guy. So I'm going to plug 0 into the original. 0 plus 1 And then 0 squared plus 2 times 0 plus 2 is going to be 1/2. This is the only number I care about, and because it goes up and then down, it's a max, local max. And again, if you want to write it 0, 1/2, that's great. Okay? So it's going from negative infinity over here. It's going up to this point, and then it's decreasing and decreasing some more back down to negative infinity. So in fact, this isn't just a local max. This is an absolute max. Is this the highest point it gets to? Cool, huh? You could call it a local max and be okay. But because this is actually an absolute max, it might be more informative to say that. All right. The good news is those problems being done, 9, 10, 11, and 12 are a lot quicker. Because all you care about is where it's increasing, decreasing. So you don't have to plug the number back into the original. You just need to find those pluses and minuses on the number line. So let's start off with f of x is x squared minus 2x plus 1. The derivative is 2x minus 2. Set it equal to 0. That means add 2, divide by 2, you get 1. All right, here's the number line. 1's the only one we care about. Here's the original derivative. So if I plug in something like 0 over here, I'll get 2 times 0 minus 2, which is 0 minus 2. That's negative. Number over here, like 2, means I would have 2 times 2 minus 2, which is 4 minus 2, and that's positive. Yeah, so decreasing, increasing. And what they want is the increasing interval. So they want the x values. So we go from parentheses 1, comma, infinity. So where means x values. Extremum values means y values. But where, if you see that in the instructions, that they want the x values and they want interval notation. Number 10, we have f of x is equal to square root of 4 minus x. So this one you're going to have to change into 4 minus x to the 1/2 power, and then take the derivative. So this is chain rule. Bring down the 1/2, subtract 1, becomes negative 1/2. And then the derivative of the inside is negative 1. Put the 4 minus x in that, and we can clean it up. So he's going to come down, but that negative 1's going to stay up there. We get 2 times 4 minus x to the 1/2 power. There's your derivative. I'm going to put a little bubble around this guy. But I'm setting them equal to 0, and once again, if you're looking for numbers where this is increasing, decreasing, we actually do care about where the denominator is equal to 0. So if we say negative 1 equal to 0, that doesn't give us anything. But if we say 2 times 4 minus x to the 1/2 equal to 0, then that could give us something. So let's divide by 2, and we get 4 minus x. Let's change it to square root. That'll make me a little bit nicer. So we divide by 2, right? That's how I got rid of it. And if I take the square of both sides, I'll get 4 minus x equal to 0. And that means that x is equal to 4. So this one, remember, this is a not equal to thing. So if you want to make that happen, that's fine. But that is the only number that goes on the number line for this problem, 4. Numerator didn't give me anything. So let's plug in numbers to the right into the derivative, like 5. And we get negative 1 over 2 times the square root of anything. It's going to be positive, isn't it? So that's negative. And if we plug in something like 3 over here, then that's also going to be negative 1 over 2 times something. And that's also positive in the denominator, so that's going to be negative. So negative divided by positive, negative divided by positive. It's just going to be decreasing, decreasing. Oh, look, not a min or max. So where is it decreasing? It's decreasing everywhere. Look at it, it's down, down. It's decreasing everywhere. So you could say that it is from negative infinity to positive infinity. But plugging 4 into this causes a problem, doesn't it? Plugging 5 into this causes a problem, doesn't it? 4 minus 5 is negative. We don't take square roots and negatives around here. So anything bigger than 4 actually is no good. So we have to change this. to negative infinity to 4. Because anything bigger than 4 doesn't even go into this particular domain. Just it's anything smaller than 4 is okay. All right. So that's why the answer here, decreasing, is negative infinity to 4, not negative infinity to positive infinity. Oh no, I'm out of paper. Hold on. I got more. Okay, 11. 2 more problems. You got it. You can do this. Or you can pause, stop, come back later, and you get time. Y equal to x squared minus 9 squared. We're going to find the derivative by doing chain rule. Bring down the 2. Thing inside, subtract 1, and then times the derivative of the inside. Okay, nothing has a negative exponent this time, so nothing moves. And the only thing I can do to clean this up, actually, you know what? I don't want to clean it up. We're going to set this equal to 0. I'm going to set each one of those things equal to 0. 2 equal to 0 doesn't mean anything. X squared minus 9 equal to 0 means that x squared is equal to 9. And then when I take the square root, I get x is equal to plus or minus 3. Here, 2x equal to 0 gives me x equal to 0 when I divide by 2. So I have 3 different numbers to put on this number line. Negative 3, 0, positive 3. And here's the derivative. I'm going to put a little bubble around them. And I'm going to take some test numbers like negative 4, and I'm going to plug it into here. So 2 times, what is that, 16 minus 9? That's positive. Times 2 times negative 4 is negative 8. So this will be a positive times a negative. That's a negative. Okay. Remember, I don't need the answer. I just need whether it's positive or negative. Negative 1, plug it in there. I get 2 times 1 minus 9 times negative 2. That's a negative times a negative, and that makes a positive. Okay, plug it in 1, I get 2, and then 1 minus 9 again, but then times 2, so this is a negative. And then plug it in 4, I get 2 times 16 minus 9 times 8. It's all positive. Okay, so it's down, up, down, up. You don't have to draw the arrows. I just like to. So it asks, where is it increasing? And in fact, it says, find the largest open interval where it's increasing. So it's increasing from negative 3 to 0, and it's also increasing from 3 to positive infinity, but this is the largest one. So I can't remember what they have as the answer. Yeah. So this is the guy that's the biggest one. But if I said, where is it increasing without asking about largest interval, you would put both. Okay? All right. And number 12. We have y equal to 1 over x squared plus 7. So again, I want to change this to x to the negative 2 plus 7 like this, so that I can do the derivative a little nicely. Bring down negative 2, subtract 1, negative 3. This one goes to 0, so all I got to do is clean this up. Negative 2 over x cubed. All right, set it equal to 0. Now again, negative 2 equal to 0 doesn't give me anything, but x cubed equal to 0, not equal to 0, gives me x 0. So the only number on this number line is 0. Now I'm going to plug these test numbers into the derivative, like negative 1. It'll be negative 2 over negative 1 cubed. Now notice, this is a cube, so this could be positive or negative after I cube it. In this case, it's negative, but negative divided by negative is a positive. And then 1, if I plug that in, I get negative 2 over 1 cubed, and that's negative. So it increases and then decreases, but I'm asking for decreasing, so it's from 0 to positive infinity. The only interval. Thank you for watching.